introduce the next talk, which is Jirka Hlinka talking about cubic barium titanate dynamic displacement disorder. Thank you.
Thank you, Mr. Chairman, ladies, gentlemen, the organizers. Thank you to be here. Allow me to be here again. I'm going to continue to talk about Drosophilas of ferroelectrics, barium titanate. The subject of my talk will be this, diffuse scattering in the cubic barium titanate. And I think the reason for that is simply I think you have not yet seen this detailed diffuse scattering in cubic barium titanate before, and I think it could be useful. I think also in the context of many other problems discussed in this conference, like, for example, domain walls in barium titanate, it's important to know what kind of disorder we have in these materials. This is the team. Involves Marek Paschak from the Department of the Electrics in Prague, Richard Welbery, Australia, Jiri Kulda from Grenoble, France, and Stefano Leoni, UK collaborator. All of them were very important in this work, which basically involves theory and experiments. So my talk I need to do a little bit of history to explain why we need new methods to go to the results which involves diffuse scattering, but also, let's say, dynamics, which is behind of diffuse scattering and real space understanding of that. So history starts long time ago. So 70 years ago already it was clear that it is titanium, or more or less clear that the titanium which goes off-center, as discussed by the previous speaker, in barium titanate, and if you think about the cubic phase, it should be the phase when the symmetry is restored. So on average, the position of the titanium is in the middle of the oxygen octahedra. But if we think about, not about Landau theory, but about statistical physics, we came easily in understanding that it's useful to think about titanium being somehow off-centered, and maybe there are some specific positions, which is the idea of eight-side disorder of titanium. And the real question is, or the real question was, because I think this question was clarified already quite a lot before, is that what's the dynamics? So how it goes in the cubic phase with this disorder? It's more like jumping from side to side between some distinct number of side positions, or it's more like rattling around the average mid position in the middle of the side. And 50 years ago, there was an important extra piece of information coming to that, and it was observation of diffuse scattering, and especially these lines, which are barely seen, but they were understood or very in detail already, and immediately after seeing them, that has to do something with the disorder of the titanium ions and the correlation between them. And originally explained in terms of phonons, but also in terms of eight-side model, and especially it was the observation in potassium niobate when the results were much more clear, the diffuse scattering was much stronger, and people have, this group, Gomez Lamborghini, they could see actually in different phases how these sheets of diffuse scattering are gradually disappearing, and in low temperature phase, rhombohedral one, they are not. So this piece of evidence seems to give a very intuitive and simple understanding of the phase diagram, the temperature phase diagram. Why we, in terms of configuration and entropy, it's very easy to understand that if we occupy one to the 8th side, there is no more diffuse scattering, no more disorder. There's some 50, I still stay 50 years ago, immediately there was some other understanding. This is the famous Wheeler paper, which tells us that this anisotropic correlation, anisotropic diffuse scattering, has something to do with harmonic interaction in the crystal, and it's something to do with dispersion curves. And I think this is the first dispersion curves calculated in many different directions in the reciprocal space in '95 by Henrik Krakauer and coworkers in potassium niobate, showing that there is not just unstable mode at the gamma point, but in many other directions in the reciprocal space, but not all. So this explains this anisotropy. So that's more or less understood since a long time. Now, about the same time as the first principal calculations appeared, there was also a question, what happens if the unstable mode at high temperatures? And this is the simulations at finite temperatures, which show us the spectrum. This is at 11 times Tc, 3 times Tc, 1.5 Tc, and almost above Tc. What is the dynamical structure factor? Is it the frequency and intensity? And we see the soft mode in barium titanate model, which is described by two-dimensional shell model at that time. And we see that originally one band, one soft mode, seems to develop as some complicated structure, like a new, what we could call central peak, and the central peak became extremely sharp at the phase transition. So actually, the original soft mode picture changed to the picture of these order dynamics jumping between different sites in the model. And there is a first shell model calculation for potassium niobate showing something similar. Here, however, we don't see developing of the central mode. We see just one mode, which is broad, but softening down. And what was pointed here was that actually there is a whole branch of the modes which is softening. But still, we don't see the central peak. And so the question is how it is in experiment. And so it was 10 years ago, it was possible to see actually some signature of the central peak in barium titanate, in the tetragonal phase. So in addition to the Slater mode, I mean the phonon frequency of the soft mode, there is a new excitation which corresponds to jumping between different sites. I illustrated here in more detail. So we are in tetragonal phase. So out of we can think about 8 minima around the center of the oxygen cage. 4 of them are occupied because we are in single domain tetragonal phase. But from time to time, we are oscillating the polarization, so it's oscillating up and down. But sometimes it goes to the position when there was the other minimum, which is no more occupied, so more. So on average, it's a little bit occupied, actually, of the other 4 sites as well. So this is what we can see in simulations. Well, so the question is actually what happens in the cubic phase. So this was tetragonal. And whether it's somehow something special related to these diffuse scattering lines, because originally, or since long time, there was debate, if we have these diffuse scattering lines, are they related just to the soft modes, or is there something which more long-time dynamics or even static disorder which exists in the material? And okay, so that's our experimental setup. The experiment was done at Argonne at the 11 IdB line with high energy X-rays, and the sample was somewhere here, so it was rotating so that we can collect the whole reciprocal space. Diffuse scattering, there is a amorphous silicon detector, and well, here are the results. So after some corrections and rescaling the calculated diffuse scattering into orthogonal coordinates, you can basically then make a cut in any direction in the reciprocal space you wish, and you really see nice these Comes lines going through the principal breakpoints, and you can, for example, look for 1-1-1 plane, and you always still see this line. That's not all. We also try to do the same thing to calculate diffuse scattering from shell model calculations. For that, we have used the existing model parameterized by Tinte and Cepiarski some years ago already, which has the correct phase diagram. I don't think I need to discuss all the details. If you wish, I can tell you later how it's done. Okay, I can skip also the discussion. We tried this before, and we have found that the diffuse scattering could be well calculated in many perovskite materials. So the next step was to go to this one. And what's important there is that actually in these images, on the left side, you have experiment. The right side is the same diffuse scattering planes calculated by this shell model calculation. These shell model calculations. Now, maybe this works as well. Yeah, I'm sorry for forgetting about the microphone. At the first side, it's basically the same. So we have very nice description of the experiment by a model. And this has an advantage that then we can look for real space configurations, the dynamics, and we can really dig in. So the calculation was done in 50 times 50 times 50 box. So we have we can make a cut through the simulating box, and each dot here, one of the 50 times 50, corresponds to one perovskite unit cell. And what is shown here is an instantaneous, it's not a snapshot of the configuration, and the color code displacement of titanium in the direction y, it's the vertical direction. So if you think about a small area, each dot is a perovskite lattice, so titanium, of course, is displayed in arbitrary direction, but we look how much only on the y component, and this is color-coded. Here is the same snapshot, but averaged over half a picosecond. So there is already some averaging, and here you can see there are stripes, which you can think about polar nanoregions or whatever, which are elongating along the y direction. So these are these longitudinal correlations, which were already understood 50 years ago. But what is important is if we do even longer averaging, let's say over 4 picoseconds, the intensity, the contrast fade out. So it means it's something which is short-lived. It exists over the time scale of picosecond. And you can even take one line like that and look in time, in longer time. The simulation was run over 100 picoseconds, but I showed just a piece of it. And you see that these clusters appear and disappear, appear and disappear. So they are more or less random. You don't see any area where it would stay for a longer time. So that's why when you average for longer than a few picoseconds, you lose the information about the cluster. Now we can do even more. We can look for the dynamic structure factor, which is intensity depending on the momentum transform and the energy, and it's as usual the double Fourier transform of the pairwise correlation functions. And we can look somewhere in the reciprocal phase, for example, along this line, what will be actually the contribution of different excitations to the diffuse scattering here. So if you wish, what is plotted here on this same line, on this line, we plot the frequency dependence of the excitations which contribute to the scattering of our X-ray beam. And we can do, so already you can see that these diffuse scattering lines, very sharp ones here and there, they correspond to a region when there is some excitations, which is very steep dispersion in this direction perpendicular to the line. We can do more. We can actually trace how the integrate the intensity part by part. For example, if you would integrate the intensity over first 10 milli-electron volt only, then you would mostly get contributions from these pieces, and you see that it has a peaks here and there, just in the position of the sharp lines. If, on the other hand, you would integrate between 10 and 20 milli-electron volts, you would integrate mostly this wave, this acoustic branch, actually the zone boundary, and this would give something which is much broader, and actually it's related to this intensity. And you can integrate everything as actually in the X-ray experiment. What we do the usual diffuse scattering experiment, and then you have the red curve, which corresponds more or less to the intensity measured in the diffuse scattering experiments. If I have time, I think I have time, I will just go along the line, along the diffuse scattering line. So that's where the intensity is strongest from that area. And then I get usual dispersion, which involve acoustic branch and optic branch. This is the last mode, the higher frequency mode, TO2 mode, if you wish. And the soft mode is here, it's the Slater mode, which is somehow for some trick making the higher contrast here. This is what you really measure, this is what we calculated. And this is done because we want to just look for the what's the spectrum at that point, for example, close to the zone center. And close to the zone center, you get this kind of spectrum. So this is from Slater mode, the titanium motion. There's acoustic branch here, and there's the motion of the barium. And the characteristic frequency of that mode corresponds to one which is measured, let's say, in infrared or hyper-Raman spectroscopy. So we know that this mode is really the soft mode which describes the dielectric constant of cubic barium titanate. So I think with this diffuse scattering data and with this picture in hands and the model in hands, we can answer quite a few questions you might have about dynamical disorder in cubic barium titanate. So we have now this diffuse scattering documented for the barium titanate as well, not just for potassium niobate. We have model. We can look for the phonons, which are contributing to that. So we are basically doing in X-ray, computer the X-ray inelastic scattering. And we can see that the intensity which is here is coming from the phonons. And especially the Comet's lines are coming from the overdamped modes, which have this kind of frequency dependence. And the frequency dependence match the dielectric spectrum, which we know to give the contribution to permittivity. So there is nothing below, nothing static. It's something which is time constant of typically of picosecond. We can also look then actually if you look for the position, let's say histogram of the displace of titanium, really in the cubic phase at that temperature, which is 100 Kelvin about TC, I forgot to say, there are 8 positions which are more probable, like most probable positions of the titanium. It's off-centered. But if you look how many of the titaniums are in these positions, only 5%. So 95% has energy which is over the barrier between them, so they are everywhere around. So most of the titaniums are just running around, so the barrier is very small. So the conclusion is that they are soft enough optic monons, steep enough to give lines, Q spectrum matches the electric one, and the conclusion there is no long-lived PNRs in cubic barium titanate. I mean the one which is the homogeneous bulk without defects. And so basically it is a displacive material with displacive cubic phase. That's my conclusion, acknowledgements, and a brief advertisement. Thank you for your attention.
Okay, so we have a couple minutes for questions. Please come to the microphones here if you'd like to ask a question. And yeah, the next speaker can come up as well. Yeah, go right ahead.
And also, I think it's I'd like to thank all my co-workers because it's demonstration that what we can do with the techniques nowadays.
But can I ask a question?
Yeah, please.
Yeah. The point is what was long been believed, that you have a coexistence of order, disorder, and displacive features. And this is what I don't see from your model or from your calculations to come out. Because as far as I can summarize the experimental situation, these two components which coexist are living on different time and length scales. And this is what I somehow miss in your approach.
Yeah, so our conclusion is that barium titanate in tetragonal phase has a clear distinction between lines, the same time scale of the order disorder dynamics, which is jumping between the minima, and the, let's say, fluctuation of the order parameters, which are small fluctuations, the ones which are described in terms of phonons. But in the cubic phase, it's not the case. It's very hard, and I would even don't know at the moment how to distinguish between them. So there is only just one dynamics, at least at 100 Kelvin above TC, it's really something, but I think it remains even down to very TC. Everything can be described in terms of anharmonic phonon, one soft mode picture at any wave vector, and yeah, that's it. Yeah, so I would say it's order disorder material with displacive cubic phase.
To some extent, I agree on what you conclude, but for instance, if you look at the EPR and NMR data, then you clearly see that there is something like an order disorder component present above in the cubic phase, above TC.
Yeah,
this is the Blind's approach, you know that for sure.
Sure, I think he mentioned as much.
Well, just in a little bit in the same vein, we did similar simulations and went very, very close to TC. Barium titanate. Of course, it's a first order, but you still have fluctuations. It's very interesting that if you're in the fluctuation interval, you get tweet, you get incommensurations and all that sort of thing, but it's only limited to an extremely small interval just above TC. So the general conclusion, I agree with you, but if you go into the fluctuation interval, Then you have these additional excitations, which are quite strong, but limited to about 1 degree or 2 degrees.
Okay, I take it as a comment. I think for the sake of the time,
Okay.
maybe if you allow me to skip it.
As a service to the broader community, can you tell us briefly what dynamic disorder means? What's a reasonable definition of dynamic disorder that's different from thermal disorder?
So, in principle, thermal disorder could be something which is extremely slow dynamics. I mean, the typical order disorder material is, for example, phase transition in solid solutions of some ions which are diffusing, right? So that's. If I think about dynamic disorder, I tried to, it was just a general keyword, but what I want to say that it can be described in terms of phonons.
Thank you. Okay, I understand.
And the number of the excitations is the same as the number of the harmonic phonons of the harmonic analysis of the material.
Okay, thank you. All right, let's thank Jirka.